This presentation treats the Hilbert Book Model project. The target of the project is the generation of a mathematical model that can be used in order to investigate the structure of the foundation and the lower levels of the structure of physical reality. I am a retired physicist. I spent my career in high-tech industry.
This lecture introduces you to the Hilbert Book Model. The model deviates considerably from the models that constitute contemporary physics. The model is strictly based on a trustworthy foundation. The Hilbert Book Model selects Hilbert spaces for that purpose. The model applies a system of Hilbert spaces. These Hilbert spaces all apply the same underlying vector space. The Hilbert Book Model represents my personal view on the lower layers of fundamental physics. A quaternionic Hilbert space can easily be structured as a dynamic model in which all past, present, and future geometric data are stored. Therefore, the corresponding space progression model becomes paginated like a book. It consists of an ordered sequence of static submodels. That is why the project got its name Hilbert Book Model. Please look at the book or paper, The Setbacks of Theoretical Physics. This is part 5 of a multi-part presentation. This part concerns systems of Hilbert spaces. Which symmetries are tolerated? How physical reality treats symmetries. How the elements of the system represent particles. How the elements of the system represent fields. The origin of electric charges and fields. The relation to the Standard Model. The Higgs particle and field. State vectors and footprints. Entanglement, conglomerates, atoms, and molecules. Two types of systems of Hilbert spaces exist. Both systems contain a member that acts as a background platform. The first type is a system of separable Hilbert spaces. The background platform owns a companion non-separable Hilbert space that embeds its separable companion. This companion archives a dynamic universe field. The floating separable members can harbor an electric charge that locates at their geometric center. A dark hole harbors the countable parameter space of the separable Hilbert space that acts as the background platform. The second type is a system of non-separable Hilbert spaces. The background platform is a non-separable Hilbert space that archives a dynamic multiverse field. The parameter space of the background platform is a continuum and therefore it is not contained in a black hole. The floating members of the system are the background platforms of systems of separable Hilbert spaces that own a companion non-separable Hilbert space that embeds its separable partner. The parameter space of the separable part of the background platform is contained in a dark hole. This configuration represents a dynamic multiverse that divides part of the underlying vector space into a set of compartments, each supports a dynamic universe. We limit ourselves to Hilbert spaces that are all derived from the same vector space. We choose 4 mutually independent directions in the underlying vector space. The axes of the Cartesian coordinate system of the number system shall be parallel to one of the chosen direction lines. This choice, therefore, leaves only a small number of different symmetry types. The exact reason why this restriction is enforced is not clear. However, it is obvious that the limitation makes it easier to compare symmetries and compute symmetry differences. The reason might be that physical reality wants to compare the symmetries. To understand the consequences of the limitation, we put the symmetries of the remaining versions of the quaternionic number system in a table whose lines we arrange with binary written hexadecimal rank numbers. We choose one of the 16 remaining versions as a frame of reference platform and place this version at the front of the queue. In the table, the fitting fermions are mentioned by name. You will notice that the anti-attribute raises a conflict between symmetries and the electric charges of the standard model. The reason might be that the anti-attribute is not measurable. You will notice that the anti-attribute raises a conflict between symmetries and the electric charges of the standard model. All these Hilbert spaces are separable and use number systems that belong to the first or second phase. The remaining system of Hilbert spaces contains a Hilbert space that can serve as a background platform. We assume that the reference version acts as background platform. The background platform must have an infinite number of subspaces. This means that the version of the number system chosen by the background Hilbert space has an infinite number of elements. It is inviting to interpret the other members of the systems as particles that move relative to the background Hilbert space. It is also inviting to interpret the background Hilbert space as a field. This field can then represent the local universe. This choice conflicts with mainstream theoretical physics that interprets this background also as a particle. That particle is called the Higgs particle. The Higgs particle is supposed to own a Higgs field. The management of the LHC may have enforced this decision because the high costs of the LHC was not corresponding the wanted measuring results. The LHC did not show any sign of supersymmetry and the LHC did not find traces of loop quantum gravity. The LHC detected a Higgs boson. No measurement ever detected that the Higgs boson, or its field, adds mass to other particles. The major value of the LHC is its huge luminosity. The LHC implements the same kind of measurement so often that even stochastic processes produce increasingly accurate values of their statistical characteristics. Several characteristics of particles are now known with accuracy in 10 or more decimals. Since they are measured, the values are specified in physical units. This still does not prove the mathematical theory that is used to interpret the measuring result. A system of Hilbert spaces that all share the same underlying vector space can act as a modeling platform that not only supports dynamic fields that obey quaternionic differential equations. The model can in principle capture all phenomena that exist in a dynamic universe. The system of separable Hilbert spaces applies the structured storage capacity of the Hilbert spaces that are members of the system. The requirement that all member Hilbert spaces must share the same underlying vector space restricts the types of Hilbert spaces that can be a member of the system of separable Hilbert spaces. In the part about change, we already restricted the definition of partial change along the directions of the Cartesian coordinate system. It appears that the coordinate systems that determine the symmetry type of the members of the system of separable Hilbert spaces must have the Cartesian coordinate axes in parallel. Possibly this is due to the existence of the primitive coordinate system in the underlying parameter space. The restriction enables the determination of differences in symmetry. Only the sequence along the axis can be freely selected up or down. It also means that partial change has a system-wide significance. This also means that only a small set of symmetry types will be tolerated. One of the Hilbert spaces will act as the background platform and its symmetry will act as background symmetry. Its natural parameter space will act as the background parameter space of the system. All other members of the system will float with the geometric center of their parameter space over the background parameter space. This already generates a dynamic system. The symmetry differences generate symmetry-related sources or sinks that will be located at the geometric center of the natural parameter space of the corresponding floating Hilbert space. The sources and sinks correspond to symmetry-related charges that generate symmetry-related fields. In physics, these symmetry-related charges are electric charges. Not the symmetries of the floating Hilbert spaces are important. Instead, the differences between the symmetry of the floating member and the background symmetry are important for establishing the type of the member Hilbert space. The counts of the differences in symmetry restrict to the short list. -3, -2, -1, 0, +1, +2, +3. The existence of symmetries and symmetry differences can be comprehended. The existence of corresponding symmetry-related charges is counterintuitive. The realization of these charges as sources or sinks of symmetry-related fields is not yet explained. All floating Hilbert spaces are separable. The background Hilbert space is an infinite-dimensional separable Hilbert space. The background Hilbert space owns a non-separable companion Hilbert space that embeds its separable partner. The vectors that represent the footprint vectors originate in the underlying spatial field. They act as state vectors for the Hilbert spaces that act as containers for the footprints. The state vector represents the vector from the underlying vector space that aims at the geometric center of the floating Hilbert space. This enables the maps of these state vectors and the corresponding footprint in the dynamic universe field. The state vector represents a vector from the underlying vector space that tries to locate the position of the geometric center of the floating platform in the parameter space of the background platform. State vectors are special footprint vectors. Together, this entwined locator installs an ongoing embedding process that acts as an imaging process of the geometric center of the floating platform onto the background parameter space. The eigenspace of a dedicated operator maps this image into the dynamic field that represents the universe. Each floating platform of the system of separable Hilbert spaces owns a single private footprint vector. The footprint vector acts as the state vector of the elementary fermion, and the probability amplitude corresponds to what physicists call the wave function of the particle. In this way, a huge amount of ongoing hopping paths are mapped onto the embedding field. Physicists call this dynamic field the universe. On the floating platforms, the hopping paths are closed. The movement of the floating platforms breaks the closure of the images of the hopping paths. Elementary fermions appear to behave as elementary modules. The conglomerates of these elementary modules populate the dynamic field that we call our universe. All massive objects, except black holes, are conglomerates of elementary fermions. All conglomerates of elementary fermions own mass. This means that the universe is covered by massive modular systems. A private stochastic process determines the complete local life story of each elementary fermion. That stochastic process is controlled in the change space of its private Hilbert space. The private stochastic process produces an ongoing hopping path and corresponds to a footprint vector that consists of a dynamically changing superposition of the reference operator's eigenvectors. This is explained in the part that treats the arithmetic of change. The dynamic superposition coefficients act as displacement generators. This means that these displacement generators define the internal oscillations of the components within the conglomerates. It might not hold for higher order conglomerates, but it holds for lower order conglomerates. Since in change space, the position is not defined, the fact that a component belongs to a conglomerate does not restrict the distance between the components. This way of defining the membership of a conglomerate introduces entanglement. Independent of their mutual distance, components of a conglomerate must still obey the Pauli exclusion principle. Hadrons can be mesons or baryons. They are conglomerates of quarks. Quarks can only bind via oscillations and via the attraction that is induced by their electric charges. Since the symmetry of quarks does not differ from the background symmetry in an isotropic way, the footprint of quarks does not deform the embedding field. So, mass does not help to bind the quarks until they reach an isotropic symmetry difference. This phenomenon is called color confinement. Hadrons feature mass. Thus, these conglomerates are sufficiently isotropic to deform the embedding field. Once configured, the mutual binding of baryons is very strong. The nuclei of atoms are constituted by baryons. Compound modules are composite modules for which the images of the geometric centers of the platforms of the components coincide in the background platform. The charges of the platforms of the elementary modules establish the primary binding of the corresponding platforms. Physicists and chemists call these compound modules atoms or atomic ions. In free compound modules, the geometric symmetry-related charges do not take part in internal oscillations. The targets of the private stochastic processes of the elementary modules oscillate. This means that the hopping path of the elementary module folds around the oscillation path and the hop landing location swarm gets smeared along the oscillation path. The oscillation path is a solution to the Helmholtz equation. Each fermion must use a different oscillation mode. A change in the oscillation mode goes together with the emission or absorption of a photon. As suggested earlier, the emission or absorption of a photon involves a switch from the quaternionic Hilbert space to a subspace that is represented by a complex number-based Hilbert space. The duration of the switch lasts a full particle regeneration cycle. During that cycle, the stochastic mechanism does not produce a swarm of hop landing locations that produce pulses that generate spherical shock fronts, but instead, it produces a one-dimensional string of equidistant pulse responses that cause one-dimensional shock fronts. The center of emission coincides with the geometrical center of the compound module. This ensures that the emitted photon does not lose its integrity. All photons will share the same emission duration, and that duration will coincide with the regeneration cycle of the hop landing location swarm. This is the reason that photons obey the Planck-Einstein relation. Absorption cannot be interpreted so easily. It can only be comprehended as a time-reversed emission act. Otherwise, the absorption would require an incredible aiming precision for the photon. The number of one-dimensional pulses in the string corresponds to the step in the energy of the Helmholtz oscillation. The type of stochastic process that controls the binding of components appears to be responsible for the absorption and emission of photons and the change of oscillation modes. If photons arrive with too low energy, then the energy is spent on the kinetic energy of the common platform. If photons arrive with too high energy, then the energy is distributed over the available oscillation modes, and the rest is spent on the kinetic energy of the common platform, or it escapes into free space. The process must somehow archive the modes of the components. It can apply the private platform of the components for that purpose. Most probably, the current value of the dynamic superposition coefficient is stored in the eigenspace of a special superposition operator. Molecules are conglomerates of compound modules that each keep their private geometrical center. However, electron oscillations are shared among the compound modules. Together with the geometric symmetry-related charges, this binds the compound modules into the molecule. On Earth, conglomerates of molecules can form living species. Living species archive essential properties in RNA and DNA molecules. Living species have their own archival system. The floating elements of the system can be interpreted as particles. In contrast, the background platform cannot be interpreted as a particle. Still, all elements of the system of Hilbert spaces are platforms that show similar capabilities and properties. All floating platforms act like symmetry-related fields, and these fields correspond to symmetry-related charges. the background platform does not show a symmetry-related field or a symmetry-related charge. Instead, it acts as a universe-wide embedding field that can be deformed by the presence of floating members. Mainstream physics considers the Higgs particle responsible for the capabilities that this presentation assigns to the background platform. In this presentation, the background platform, including its non-separable companion, implements the origin of the gravitational potential via the action of spherical shock fronts that are generated by actuators that cause isotropic pulses. Field excitations cannot enter or leave black holes, but the Hilbert spaces that represent elementary fermions may hover over the enclosed region of the black hole. So, part of the footprint of the elementary particle may be mapped into the region of the black hole. The mass of the black hole attracts nearby elementary fermions. Together with the effect of hovering, this may enable the growth of black holes and the merge of approaching black holes. It may also explain the merge of a black hole and a dense star. The Hilbert Book Model embraces the special set. Via the selected version of the associative division ring, this special set determines in detail how the separable and its companion non-separable Hilbert space behave. For physical reality, one of the members of the system of separable Hilbert spaces plays the role of background Hilbert space. This special role confuses many scientists. The Hilbert spaces inherit their symmetry from the selected version of the associative division ring. The difference between the symmetry of the Hilbert space and the symmetry of the background Hilbert space defines an electric charge that becomes a property of the floating Hilbert space. The electric charge represents a source or a sink of a corresponding electric field. The dynamics of the floating Hilbert space determine the dynamics of its electric field. Quaternionic differential equations describe the dynamic behavior of the electric field. The system of non-separable Hilbert spaces invites the compartmentalization of space. This idea stimulates the ideas of a holographic universe and parallel multiverses. This will be subject of the next part of this multi-part presentation. This ends part 5 of a multi-part presentation. This part concerns systems of Hilbert spaces. Which symmetries are tolerated? How physical reality treats symmetries. How the elements of the system represent particles. How the elements of the system represent fields. The origin of electric charges and fields. The relation to the Standard Model. The Higgs particle and field. State vectors and footprints. Entanglement, conglomerates, atoms, molecules. Part 6 concerns potentials, gravity, shock fronts, refraction, electronic imaging, holographic systems. Holographic universe, multiverse, partitions of outer space.